let me just recall the, I think I should write here, recall the main point. What we are looking at is x and y are two nonlinear spaces over F, where F is always R or C, either real or complex nonlinear spaces, and we looked at Bxy. We looked at Bxy, which we call as the collection of all bounded linear transformations from x to y. Okay, all bounded linear transformations from x to y. We observed that Bxy is a linear space, that is, it is a vector space, and it is indeed a normed linear space. Okay. So that's the main thing that comes out. If you have two nonlinear spaces, the set of all bounded linear transformations from x to y is itself a nonlinear space, where recall the norm of the transformation T for T in Bxy, we define the norm of T to be the maximum, or I should say supremum, x not equal to theta x, x belonging to x of norm Tx by norm x. Okay. So with this norm, that became a norm linear space, and this is the y norm, this is the x norm. Okay. The question that we asked and just answered without giving a proof last time was whether Bxy is a Banach space, and I claimed that it is a Banach space if y is a Banach space. So the main theorem is Bxy is a Banach space if y is a Banach space independent of the fact whether x is a Banach space or not. So, irrespective of whether x is Banach or not. Okay. I am going to now look at a proof of this, because this is the starting point of functional analysis, and I am going to look at a proof of this theorem because it brings out many ideas that we should keep in mind when we deal with linear transformations, etc., etc. Okay. So let's look at a proof of that. So what is our aim? Our aim is to show that Bxy is a Banach space. Okay. We will see exactly at which point the fact that y being a Banach space comes into play. Okay. So well, let's keep going. We want to prove that Bxy, I'll go slowly with the proof. I'll write Banach space as B space. We want to prove that Bxy is a Banach space. What does that mean? We must show it's a complete norm. We already have a nonlinear space. To show that it is a Banach space, we have to show that it is complete. So that is to prove that Bxy is complete. Of course, with that norm. Okay. What is it meant by saying that something is complete? We have to show that every Cauchy sequence has a limit. So, that is to prove that every Cauchy sequence in Bxy converges in Bxy. So, what does that mean? So, let us make clear what is it that we want. To prove that, given if Tn is a Cauchy sequence in Bxy, it must converge. That means there exists T in Bxy such that Tn converges to T. That means the norm of Tn minus T, the difference must go to 0, such that norm of Tn minus T tends to 0. Okay, so what we have to do is, must start with any Cauchy sequence, capture that fellow T, sum over the other, capture that T to which it converges. So, your main job is locating that T given the Cauchy sequence Tn. Okay. So, therefore, we start with a Cauchy sequence. So, okay, so let us start, therefore Tn be any Cauchy sequence in Bxy. So, our job is to go ahead and find out that T. So, first of all, let us note down. So, this, remember, this is our final, this is our actual goal. If Tn is any Cauchy sequence in Bxy, we want to show that we can find a T in Bxy, that the Tn converges to T in Bxy, okay, with all in that norm. Okay. So, let Tn be any Cauchy sequence. Well, let us note down what does that mean. That means Tn and Tm get closer and closer as we go far off in the sequence. So, how do we write that? So, let me note this part. Therefore, given any epsilon 1 positive, I will put an epsilon 1 so that I may have to adjust with any general epsilon. Given any epsilon 1 positive, there exists a stage which depends only on epsilon 1, such that if we go beyond that stage, the difference between Tn and Tm is less than epsilon 1. Let me call this as 1. So, that is what is given to us, that is the only given information, that Tn is a Cauchy sequence. That means that information is given. From that we must generate a T such that Tn minus T in norm goes to 0 and then goes to infinity. So, my job is to look for this T. So, what is this T I am looking for? It should be in Bxy. It must be a bounded linear transformation from x to y. So, first of all, it must be a transformation from x to y. So, therefore, it must transform a vector in x to a vector in y. That is the minimum thing that it should do. So, we must say we must find what is the action of T. If at all such a T existed, we will find out what is the action of T on any x. Okay. So, if there existed such a T, we don't even know whether there existed. We say if there existed one, how should he look like? Then we say, okay, there is one fellow who looks like this, hang on for dear life to that fellow and show indeed he satisfied all my requirements. Okay, so if there exists, if there was such a T, what do you mean by such a T? This is what we are looking for. If there was such a T, then what should be, okay, then it must first of all be a transformation from x to y. Hence, we must know what is t of x for every x in x, and this must be in y, and this tx must be in y. So, in order that it is a transformation from x, so we must say what is t of x, and the result must be in y. So, for every x it must produce a tx which is in y. So, first of all, to know the action of t as a transformation, we must find out what is t of x for every x. So, how are we going to find that out? Remember, we are saying if there existed such a t, we do not even know whether there exists such a t. If there existed such a t, then norm Tn minus t will go to 0. Okay, so when I say if there existed such a t as in star, since t is as in star, we must have norm Tn minus t tends to 0 as n tends to infinity, if there exists such a t. In that case, for any x, hence for any x in x, we have t n x minus t x, that is equal to, now what is this norm? What is this norm? This is the bxy norm. What is this norm? Y norm. So, we must keep that part in mind. T n x minus t x is actually T n minus t of x. That is how we defined addition, scalar multiplication, etc. in bxy. And because Tn is in bxy, and because we are assumed that if there was a t in bxy, so t is also in bxy. So, Tn is in bxy, t is in bxy, therefore Tn minus t is in bxy, because bxy is a vector space. Okay, therefore, Tn minus t is in a bxy, that means it is a bounded operator. If it is bounded operator, norm of ux is always less than or equal to norm of u into norm of ux. Okay, so this is less than or equal to norm of Tn minus t into norm of x, because Tn t belong to bxy, and hence Tn minus t belongs to bxy. Is that correct? Okay. But because we are assuming star, what should happen to norm Tn minus T? It must go to 0. So this whole thing will go to 0 and this cannot be negative, and therefore that is forced to go to 0. So this tends to 0 because norm Tn minus T goes to 0. And therefore Tnx converges to Tx. So therefore Tnx converges to Tx in Y, and hence Tx is equal to limit n tending to infinity Tnx. Right. So therefore this, what our analysis says is, if at all there existed a T, its action on any x must be the limit of the actions of the Tn. Okay. So the conclusion is, let me call it as 2. Therefore if there exists such a T, then Tx must be defined as in 2. I still do not know whether there is such a T. I am just talking in vacuum perhaps. There may not be any such T. If at all there was such a T. Now I have something in terms of known. The Tn's are given to me. So I don't even know whether the right hand side limit exists. If by chance they existed, then I have gotten hold of T. If I know, given this Tn, if I can show that for every x this limit exists, then I will define that limit as the new transformation. So therefore my job is not, at least now, instead of searching for this T in darkness, I have somewhere to look for this T. What I do is, for every x I look at Tnx and see, because Tn's are given, for every x I look at Tnx and see whether the limit exists. If I am lucky and if a limit exists, I will define that limit to be the action of T on x. Okay. So therefore we do not even know a priori, given the T, given the Tn, whether the RHS limit exists. If we can show that the RHS limit exists for every x in x, then we can define T by 2. Okay. So let us backtrack and see what we have done. We are given only this sequence Tn and we are given that it is Cauchy. We want to find a limit for that. We did not know how to find a limit. We said if there was a limit, it must be a transformation from x to y to start with. So if it is a transformation from x to y, it must convert every x in x to a y in y. What should be that conversion process? And we said if at all there was a limit, the conversion process must be this. But then I do not know whether this limit exists, and therefore I will go first establish that limit exists. And once I establish that limit exists, I have gotten hold of a transformation. Okay. He is not yet guilty. He is arrested for substantial evidence. Okay. Circumstantial evidence is there against him, but case is Well, there are people who have been hanged for circumstantial evidence, but in mathematics you don't hang that person unless you prove he is the fellow. So he says, we suspect you, we will examine you, and we will establish that you are the right culprit here. Okay. So that's what we are going to do. So our line of argument will be as follows. So our line of arguments. One, first establish that limit n tending to infinity t in x exists for every x in x. Okay. Then define t mapping x to y as t of x is equal to limit n tending to infinity t n x as suggested by our argument. Then what? We have only got this as a transformation from x to y. We have to establish that it is a bounded linear transformation. So, show that t as defined in 2 is a linear transformation first. Then 4, show that t is bounded. So we would have now made inroads in our proof. If t is a Cauchy sequence, we have now gotten hold of a t in bxy. The last step is that t we got is indeed this thing. The last step is show that show that indeed now I can write this because Tn I have established Tn is given to be in bxy. In the previous step I would have established that T is a bounded linear transformation, so it is also in bxy. If Tn is in bxy, T is in bxy, Tn minus T is in bxy, so I can start about this norm and that goes to 0 as it goes to infinity. So first get some feel for who we should look for as the candidate for the limit, get him, and he slowly step by step establish that he is indeed the right candidate. Okay. So that is the line of argument in many of the proofs. Whenever we are looking for a limit, we don't know who the limit is, then we say who is the possible candidate, capture him and say such a possible candidate exists. If there was a possible candidate, how should he look like? And then we say hey, there is indeed a fellow like that, catch him, and then say that possible candidate is indeed the candidate by verifying all that is required for the candidate that you are looking for. Okay. So now the rest of the proof is only going through routinely one by one of these checks. Okay. So now we have established that there is a transformation provided we have this, right. So that's our first thing. Now there you will precisely find that the fact that y is Banach comes into the picture. So we want to show in step 1 that this sequence converges for every x. So take an x and look at t and x. Where are they living? They are living in y. If I show that the fact that Tn's are Cauchy forces Tnx to be Cauchy, Tnx will be a Cauchy sequence in y is Banach and therefore it will converge. That is where the role of y being a Banach space comes into the picture. Okay. So, step 1. So, the proof of 1, I will write proofs one by one. I will just indicate the proofs. So, now it is we use the fact that Tn is Cauchy to establish that Tnx is Cauchy in y for every x in x. Okay, so it's very obvious, because norm Tnx minus Tmx is less than or equal to norm Tn minus Tm, but norm Tn minus Tm is small, and therefore we are done. Okay. So therefore, so what do we get? So we have norm Tnx minus Tmx. If you want to show that Tnx is Cauchy, all we have to show is that Tnx minus Tmx can be made small for sufficiently large n and m. Now this is equal to norm of Tn minus Tm into x, which is less than or equal to norm Tn minus Tm into norm x. That is because Tn and Tm are bounded, and therefore difference of two bounded linear transformation is bounded linear transformation, and therefore that is true. Now this can be made small. This is our first fundamental thing. So therefore this is less than epsilon 1 into norm x for n and m greater than or equal to n epsilon 1 by 1. So therefore given any epsilon, choose epsilon 1 to be epsilon by norm x, so that will be less than epsilon. Okay. Now only thing is you are going to divide by norm x. What if x is 0, the 0 vector? Well, if x is the 0 vector, t and x are all 0 and are automatically converging to 0. There is nothing to worry about. So we have to worry only about when x is non-zero, because a linear transformation is always 0 at the 0 vectors. So therefore, so given epsilon greater than 0, choose epsilon 1 to be epsilon by norm x. Here I assume that fact that x is non-zero, and therefore we have n epsilon 1, but epsilon 1 depends on epsilon such that n m greater than or equal to n epsilon implies norm Tnx minus Tmx is less than epsilon, and therefore Tnx is Cauchy sequence in y, but y is a Banach space. This is where we use the fact that y is a Banach space. Therefore Cauchy sequences must converge. Therefore Tnx limit exists in y, and therefore we are done with this. First establish that this limit exists, and therefore we can now define t. Okay, the first two steps are done. Second step follows automatically if you finish the first step. The limit exists, therefore I am going to define the transformation Tx as limit n tending to Tnx. Now the next step is linearity, which is very obvious, because limit is a linear operation. Limit of a sum is the sum of a limit, and limit of a constant multiple is constant multiple of the limit. So those things follow automatically. So let us now write 3 I will now work within this space because okay, I will work within this Cauchy. Let me keep this, okay. So I will work within this space, I will go on erasing it, okay. So now we come to 2. 2 is also over, so 3. Once you have the limit, 2 is defined, 2 is only definition. 3. We want to show that t is linear. What does that mean? We want to show that tx plus y is tx plus ty and t of alpha x is tf. So t of x plus y, by definition, it is limit n tending to infinity of Tn of x plus y, okay, because t of u is limit of Tn of u, that is the definition of t. Now I know Tn is linear and therefore I can split them. Here I didn't know whether I can split it or not. I now forward all this problem to some known linear fellows, these are the Tn's. This is equal to limit n tending to infinity of Tnx plus Tny, because Tn is linear. Now limit of a sum is the sum of a limit, so it is limit n tending to infinity Tnx plus limit of n tending to infinity of Tn of y, and by definition limit of Tnx is Tx and limit of Tny is Ty. So that is equal to Tx plus Ty by definition of T. By definition of T is this 2. So sum is over and the scalar multiple, we should now look at T of alpha x. Again it follows the same pattern. We have T of alpha x is equal to limit n tending to infinity of Tn of alpha x, because that is the definition of T. T of anything is limit Tn of that. And now Tn is linear. So this is alpha Tnx because Tn linear. Now constants can be pulled out of limit. So it is alpha times limit n tending to infinity Tnx, which by definition is alpha Tx. So we have both this and therefore we can tick 3. We have shown that T is a linear transformation. Now we want to show that T is bounded, okay. That is the next step, and finally clinch the issue by saying I have found a fellow, now I am going to establish he is the fellow. Okay. So far I have still not found the fellow. I have found the fellow only when it is in Bxy. So until that stage I am still not sure whether he lives in this world or it is an imaginary person, okay. So now to show that it is a bounded transformation, I use a property that any Cauchy sequence is bounded. Any Cauchy sequence is bounded. What do I mean by that? If you have a Cauchy sequence, let us say any Cauchy sequence of real numbers is bounded. You know that? Know that fact? Any Cauchy sequence of real numbers is bounded. Let me just indicate, this is aside because we are doing functional analysis, so we assume that we know real numbers. So therefore we will hide this fact somewhere. Suppose I have a sequence of real numbers which is Cauchy. What does that mean? I can make that difference as small as possible, okay. Okay, so I can make the difference less than 1, right, for say n and m greater than or equal to some n1, that will be less than 1, and therefore if I now look at what can I say about that. This is true for if I put for m any value greater than or equal to n1, I have put n1, so that will still be n1. But now that an1 is a fixed real number, one term in that sequence. Now what can I say about mod an minus mod an1? That is less than or equal to mod an minus an, and that is less than 1, right, and therefore mod an is less than or equal less than 1 plus mod an1 for all n greater than or equal to n1. What does that mean? I have this sequence a1, an1 minus 1, an1, etc., etc. These fellows are all bounded by this constant k, but these are only finite number. So there is one constant, that is the maximum of the mod ai's for 1 less than or equal to I less than n1. These are below some number, these are below some number, so both of them will be below the maximum of these two, and therefore the sequence is bounded. So this is a very simple common sense argument. So a sequence of real numbers is, if it is Cauchy, it is bounded, right. So now what we will see is, if a sequence is Cauchy, the norm is a real number Cauchy sequence. If Tn is Cauchy, then norm Tn, which is a sequence of real numbers, I am just looking at the norm, that will be a Cauchy sequence. If it is a Cauchy sequence, it has to be bounded. Okay, so if, since Tn is a Cauchy sequence, we have norm Tn is a Cauchy sequence of now real numbers. Whenever you have a Cauchy sequence in a nonlinear space, the corresponding norms will form a Cauchy sequence of real numbers, because norm Tn minus norm Tm is less than or equal to norm of Tn minus Tm, and there the story ends. Okay. So if the norm Tn is a real number Cauchy sequence, and any real number Cauchy sequence must be bounded, so implies norm Tn is bounded, it implies there exists a k such that norm Tn is less than or equal to k for all. Any question? So that's the simple idea, that if you have a Cauchy sequence of real numbers, it should be bounded, and if you have a Cauchy sequence of any nonlinear space, the corresponding norm sequence is a bounded sequence. Right, what do I get out of this? Well, from this I get that norm Tn x is less than or equal to norm Tn into norm x, which is less than or equal to k times norm x for every x in x, right. Norm Tn x is less than or equal to norm. So therefore, what can I say about limit n tending to infinity of norm Tn x? Since every term is less than or equal to k times norm x, the limit must also be less than or equal to k times norm x for every x. Every term is less than this, so therefore limit is this. But then by definition of this, if Tn converges to T, the norm Tn will converge to norm Tx, and therefore this implies by 2 norm Tx is less than or equal to k times norm x for every x. That is precisely the meaning of that T is bounded. Okay. There is a constant such that the new length divided by the old length is under control. Okay. This implies T is bounded. This is the definition of boundedness. Okay. So now I have done practically everything. We have now captured a possible fellow in Bxy who could be the culprit. So what is the last step? He is indeed the culprit. Now what should we show? norm Tn minus T goes to 0. Okay. So, in order to find the norm of something, we always look at the action of that compared to the old one. How do you find the norm of U? We compare norm of the changed ratio to the norm of the original fellow. That ratio should is what always we should be worry about. Okay. Now, what do you get from here? For any x, I will just quickly finish this up. For any x in x, norm Tnx minus Tmx is less than or equal to norm Tn minus Tm into norm x, that is known. But now norm Tn minus Tm can be less than epsilon 1. So, that is less than epsilon 1 times norm x. For what? For n and m greater than or equal to n epsilon 1, right. I go on increasing the m and let m go to infinity. When m goes to infinity, what happens to Tmx? It will go to Tx. So, let m go to infinity, keeping n greater than or equal to 1. Keep any n greater than or equal to n1, let m go to infinity. Since this goes to Tx, the corresponding thing will go to, and that will be in the limit, the less than can become less than or equal to norm x, right. Therefore, norm of Tn minus Tx is less than or equal to epsilon 1 times norm x for every n greater than or equal to n1. What does this say about norm Tn minus T? Remember, the ratio will be what? At most epsilon 1. Okay, the least upper bound is what is called the norm. So, the norm must be less than or equal to epsilon. So, that says norm Tn minus T is less than or equal to epsilon 1 for every n greater than or equal to n1. So, given epsilon, choose epsilon 1 to be epsilon by 2. So, given epsilon, choose epsilon 1 to be less equal to, and do all these things, you get norm Tn minus T less than epsilon, because this is epsilon by 2 for every n greater than or equal to some n, and that is precisely what is meant by Tn converges to T. Tn converges to T if the difference in the norm can be made small. So, first we got the transformation, then we established E is in there, then we established this. So, we went step by step. We want a transformation, we want him to be there, and finally we want him to be the limit, and we quietly zeroed in on him and killed him. Okay. So, that is, see, these are the steps, basic ideas involved. But you do not know the limit, try to capture a fellow. Make sure he is there in the right space, and then make sure he is the limit. Okay. So, therefore, we have now established a theorem that if x and y are non-linear spaces, and if y is a Banach space, then the space of all bounded linear transformations from x to y is a Banach space. This is a fundamental theorem on which rests the rest of functional analysis. Okay. Okay. So, now I have freedom to erase everything. Yeah, probably a book would have finished it off in 5 lines or 6 lines, but I took the time out to do this in detail, because it is the first major theorem that we are proving in non-linear spaces. Okay, so the moral is our theorem. Bxy is a Banach space if y is a Banach space. Okay, this is the. Now, one special case of this is what's of great importance. But Bxy itself, in particular, okay, let me make some special cases. Well, we would like to look at operators, which means mapping from a space to itself, and therefore I would like to have Bxx, which is Bx, which I denoted Bx. Now, if that has to be a Banach space, y has to be a Banach space, which means x has to be a Banach space because I am taking x is equal to y. So, if x is a Banach space, then Bx, which is the space of all linear operators bounded from x to x, is a Banach space. This is a very important Banach algebra. Okay, we will see. So, therefore, if we take x equal to y, a Banach space, then Bx, the space of all bounded linear operators on x is a Banach space. Now, in this only we will study how far I can push the matrix ideas into this. A matrix, a square matrix is a linear transformation from a vector space into itself. Now, I have pulled the vector spaces to the non-linear space level, and I have to now pull the matrices to bounded linear operators. So, therefore, in this space how far I can push matrix theory, the generalized versions of matrix theory. So, that is the operator theory. Okay. There are lots of difficulties that we will encounter because it is an infinite dimensional space. Okay. Maybe now I have raised that question, we will come to this question later. Let me throw this question. Okay. Suppose I give you a matrix, let us assume it is a complex matrix, okay, because it is easier to work with the complex numbers since it is an algebraically closed field. Suppose I give a complex matrix, we say it must have at least one eigenvalue, and in fact it must have, if it is an n by n complex matrix, it must have n eigenvalues because probably some of them repeated. Why is this true? Yeah, fundamental theorem of algebra, because the eigenvalues come out as the roots of the characteristic equation, which is a polynomial equation of degree n, and the fundamental theorem of algebra says that in a complex, in an algebraically closed field like complex numbers, any system of equations, any polynomial equation of degree n will have n roots, and this may be repeated, that does not matter, but there should be n roots. Now, if you want to go to infinite dimensional spaces, you are in trouble, because now the matrix is infinite, infinite number of rows and infinite number of columns, even assuming that we have the discrete situation. Then even if we assume that I am going to carry on the analogy, and in place of a polynomial I will have an, what will I have for characteristic equation? I got a polynomial of degree n because I had n columns, right, and n rows. But if I have infinite number of columns and infinite number of rows, I will have a infinite series. But if you have an infinite series, there is no reason why it should have a root. For example, if you look at the exponential series, it does not vanish. The e to the x, suppose I have the series like the e to the x, something does not vanish anywhere. So, there is no root. So, the existence of eigenvalues itself is fundamentally under question when we move to infinite dimensional spaces. Even with the simple analogy, it is going to get more complicated. Okay. So, therefore, matrix theory cannot be pushed as you like in infinite dimensional spaces, but we will say that there are certain special class of operators where we can verbatim push matrix theory. The knowledge of our matrix theory can be verbatim pushed to a sub algebra of this algebra of bounded linear operators. Okay. That is a little farther away. It is just to say this will become important when we try to look at what are the generalizations of matrix theory that we can do. Okay. So, that is one special case. The second special case is we want Y a Banach space. The simplest Banach space we know is the numbers themselves. So, we take Y to be F. Remember, we say that F is complex or real. So, if it is a real, if X and Y are real, if X is a real nonlinear space, take F to be R. If X is a complex nonlinear space, take F to be C. Then automatically it is Banach space. The real numbers is a complete space and the complex numbers form a complete metric space. So, therefore, they are both Banach spaces, and therefore, Bxy, Bxf is a Banach space for every nonlinear space over F. For every nonlinear space, the Bxf will be a Banach space, and this is denoted by X star. And this is called the dual of X. Actually, it is the topological dual, and we will talk about only the topological dual. When the algebraic dual, we will not talk about. Okay. And any F belonging to Bxf or X star now already is called a bounded linear functional on X. Okay. And the norm, of course, is mod Fx by norm X. The Y norm becomes simply the modulus norm because Y is numbers norm. Okay. And as the name itself suggests, is the functionals that one is mainly interested in functional analysis. It is always this bounded linear functionals that play a crucial role in functional analysis. Okay. Now, before anything, let us start with some very simple examples of this very special case where Y is the simplest nonlinear space I can think of over F, namely the F itself. Okay. So, let us look at this space X star and look at number of examples. Okay. So, for any example I need a nonlinear space. For any X star example I need a nonlinear space which will be real or complex nonlinear space, and then I have to look at the linear functionals and bounded linear functionals. So, the simplest, if you want to look at a nonlinear space, first I should look at a vector space, and the simplest vector spaces I know are the R2, R3, Rn in general. So, okay, so the first series of examples. So, first consider the vector space Rn, okay. N is some positive integer. Now, I have not put norm yet. Remember, I have not yet put the norm. I am looking only at vector space. So, the first thing I can only talk about linear functionals because I can't talk about still bounded until I put norm. So, I am this BXF, I am still looking at only the linear part of it. So, what say let us look at a linear functional F on Rn. What does that mean? That means from every vector this F filters a number. It is linear functional, it must take every vector to a number. So, it is some kind of a number code is given to every vector. So, that is F maps Rn to R. A linear functional maps it to the field F, the field F is now R because we are looking at Rn. So, we have a linear functional of R, that is F map, and F is linear, that is F preserves superpositions, F of x plus y is x, F of x plus F of y, and F of alpha x is alpha f. Now, we learned in linear algebra that whenever you have anything linear on a vector space, a complete knowledge of it is captured if you sample it on the basis. Okay, so therefore, all you have to do is to get a knowledge of this F, we have to simply sample it on a basis. So, let us say, let us take a standard basis, let E1 be 1 0 0 0, E2 be 0 1 0 0, and so on, En be 0 0 1 be the standard ordered basis for Rn. Then all you have to do is see what this the functional does, what is it that it filters for E1, what is it that it filters for E2, and so on. Okay. So, let F of Ej, F of any vector must be a number, so it must be a number. So, let us say it is F of j, j equal to 1 2 up to n. Okay, then for any x, x1, x2, xn in Rn, we have x is x1 E1 plus xn En, and that implies f of x is f of the right hand side, but f is linear, so superpositions are split out. So, it is x1 fe1 plus etc xn fen, and therefore, that is x1 f1 plus x2 f2 plus xn fn. So, therefore, the moment you know the coordinates and the moment you know the action of f on the base vectors, you know the action on the x vector also. Because if I know the action of f on the base vectors, I know this little f1, little f2, little fn, and the moment you give me the vector, I know its components, and therefore, I can immediately write down what f does on this vector. So, therefore, this linear functional is simply captured completely by sampling it on the base vectors. Okay. Now, I am going to look at I am going to write a vector f from these sampled numbers. This vector f stores the sampling that we have done on the basis vector. So, this is the storage of that information, the sampled information. Now, that is a vector in Rn, because there are n components, each one of them is a real number. So, starting from the linear functional on Rn, I have constructed a vector in Rn. We will see that role later. Okay, so all right. Anyway, so what does that mean? Let me put it this way. Okay, maybe I will do one more thing, and then we will summarize. We will continue the summaries in the next class. But so what have we done? We started with an f, which is a linear functional on Rn, and then from that we constructed an f in Rn such that the action of fx is simply summation xj fj j equal to 1 t. That is what it is. Okay. Now I am going to do something very. Look at mod fx. What is that? Modulus of summation j to f j, right? Now I have this whole host of inequalities. Cauchy-Schwarz, Holder's inequality, and so on and so forth. So let 1 less than or equal to p less than infinity. Let us say first this 1 less than p less than infinity. Okay. Then Holder's inequality gives me that mod fx is less than or equal to summation mod xj to the power of p to the power of 1 over p j equal to 1 to n times summation j equal to 1 to n mod fj to the power of q to the power of 1 over q. What is q? 1 over p plus 1 over q is equal to 1, the conjugate index. Okay. So 1 over p plus 1 over q equal to 1. So once you give p, you can get q also, the corresponding. Now that says mod fx by norm x, the p norm is less than or equal to the q norm of f. Of course, for x not 0. Okay. Now this simply says the new length versus the old p length will be less than or equal to the q length of the f you constructed. Most importantly, it says the ratio of the new length there is no choice, it is only modulus, if the field is f. But in Rn you have several choices of norm. Whatever this p norm you choose, the ratio of the new length to the old length is bounded. That means f is a bounded linear functional if we choose Rn and the p norm. Okay, that is what we call as LPN. Okay, so therefore f is a bounded linear functional on LPNR for 1 less than p less than infinity. We will come to equal to p and equal to infinity later, 1 less than p less than infinity, and in fact norm of f is less than or equal to norm of fq, because this is bounded by this, the smallest bound is called the norm. This is one of the bounds, therefore it has to be less than or equal to norm fq. So very strange. So what we have done is, whatever linear functional you take on Rn, treated as a linear functional on LPNR, it will be bounded, whatever p you choose. Okay. So every linear functional is bounded linear functional in every one of these LP n when 1 less than p less than infinity. Okay. So, now what is ahead? What we have done is the following. On the one hand, we have this x which is our LPNR, the given non-linear space. On the other hand, we have this x star, and what we have said is given any f here, there is a corresponding f there. Given any linear functional there, because it is a bounded linear functional, therefore it is a linear functional. Because the linear functional, that little f can be constructed there, and therefore every f can be converted to this little vector there, and in such a way this norm is dominated by the q norm of this f. So, okay, I am sorry, I have drawn the wrong pictures. So, I have to draw the correct pictures. Okay, here is x, which is LPNR, corresponding to that is the LQNR, right? And now I take x star, and then if I have an f, I have a corresponding f there. Okay. So, corresponding to a linear functional, there is an f here which is an LQN, and this norm here dominates that the norm of this in this space. What we will see is it is exactly equal. It is not even greater than or equal to. It is exactly equal. So, the first thing that we will show next time is that it is indeed equal, and that it is a two-way traffic. Given the f there, there is an f here, given an f here, there is an f there, and this two-way traffic is 1 1. What does that mean? Everything here can be coded as something here without losing superpositions, without losing the norm. So, therefore, this can be essentially identified with this. This is what is as a isometrically isomorphic. So, therefore, the conjugate of this space can be identified. So, the conjugate of LPNR is the LQNR. Okay. That is why the numbers p and q are called conjugate numbers. The dual or the conjugate space of LPNR is the LQNR. Okay. Analogously, we will see that the conjugate space of LPNC is LQNC, complex situation, and in fact in the Lebesgue space of integrals or measurable functions, the big LP over an interval is the conjugate space is the big LQ. Okay. So, that the P and Q hold on to each other as the conjugate distinct. So, the functional space can be identified with actually the original vector space itself. Both have the same vector space Rn. The only thing that has changed is the norm. The original vector space had P norm. The functional space is identified with the same vector space, but with the Q norm. If P equal to Q, that is half. P equal to Q equal to half, then L2 its conjugate is identified with itself, L2. And the generalization of this theorem in Hilbert spaces is what is known as the Riesz representation theorem. The most general version of that is called the Riesz representation theorem. So, what we will do next time is we will complete this identification on the finite dimensional spaces. The p equal to 1 and infinity we will investigate later separately. Okay. So, that will be the first major example of our dual space or the conjugate spaces. But then we will proceed from there and see some other examples. See, the things get complicated when you go to infinite dimensional spaces. For example, if you want continuous functions space, it is a non-linear space. What is its dual? It is a more complicated thing, and so the duals, the functional spaces become more and more complex when we get into infinite dimensional spaces. Finite dimensional spaces are the easiest one. But as in this case P equal to Q equal to 2, it's the easiest case. The thing collapses into itself. X star collapses into X itself, because the functional space is this, but this can be identified with this, but this is the same as this with P equal to Q. So the X star collapses can be identified with X itself. Such fellows are called Hilbert spaces. Okay, that is the Hilbert space theory, where things are easy. That's why the best place to work is Hilbert space. Okay, that is the most comfortable space where we work. We have the dot product, we have the inner product, we have orthogonality, we have orthogonality. The dual space is itself. All the things that we do basically can be carried over there, and in that space the analysis of the BX matrix theory, pushing it becomes much easier. Okay, so that's all, that will be our goal. Okay, one thing is how to push matrix theory, the other thing is how to push our normal analysis to infinite dimensional analysis. So these functionals will be our main heart. Okay, it's like what do I call it's the it's like the lifeline of this whole subject. Okay, basically what a functional does is it filters, it's like a filter. It filters one information about every vector, and that information is coded as a number. Okay, so you can already see it's a digital world. Okay, the functional analysis is aiming towards digital world. It gives you numbers to organize, to look at very complex abstract nonlinear spaces. X can be anything, but then finally you bring it down to numbers, and probably that's where Kronecker says God gave us integers, all else is man's work. So however complex it is, we want to bring it to numbers, because that is the only thing that we know how to work with. All the things we say is only Maya. Finally we'll bring it down to numbers. If it is not number, we don't know how to even do anything with it. Okay, so therefore sometimes this may be wrong. Right, we are trying to get into the Heisenberg's uncertainty situation, trying to analyze quality in terms of quantity. The moment you go to quantify that quality, you are disturbing it. Okay, you might not get the quality. Okay, so whether these things filter out all the information, or whether this is the way to filter out information, that's a different ball game. But today's world, in the computing world, there is no choice but to convert everything to numbers. Okay, and these functionals do it. Different functionals do different ways of filtering information. Okay, so I'll continue with this functionals in the RN in the next class.